Hi guys, this is the EdExcel A-Level Further Maths paper from the June 2019 series covering the Further Mechanics 1 section. Okay, so examiner report wise, well, this paper basically was a chance for people to demonstrate their understanding of a lot of the topics assessed. Now, interestingly, the best work included clear diagrams with structured working that was easy to follow. There were a large number of candidates who could reach their given answers, but they were less confident in applying their knowledge where there was no given target. So if there wasn't a sure that question, they were struggling quite a lot. They could apply basic principles, but they were uncertain with what to do with those results because they don't really understand the topics inside out. There were some weaker candidates who were not comfortable with working with vectors. Everything that, in terms of vectors, that you should know from this paper is covered in either the A-Level Maths or the A-Level Further Maths course spec. If you ever use a value of g, the final answer should be given to 2 or 3 significant figures, but a lot of people lost accuracy marks because they over-specified final answers, which I think is a very interesting common theme in a lot of these papers. Question number 1. We have figure 1 over here, which represents the plan of part of a smooth horizontal floor, where W1 and W2 are 2 fixed parallel vertical walls. The walls are 3 meters apart. A particle lies at rest at the point O on the floor between the 2 walls, where the point O is d meters and d is greater than 0 but less than or equal to 3 from W1. At time t equals 0, the particle is projected from O towards W1 with speed u meters per second in a direction perpendicular to the walls. The coefficient of restitution between the particle and each wall is 2/3. The particle returns to O at time t equals capital T, having bounced off each wall once. So the particle starts here, goes to W1, then goes to W2, then goes back to O. We have to show for part A that t equals 45 minus 5d over 4u. The important thing in this question is to recognize that for part A, E is equal to the speed of separation over the speed of approach. Okay? And having said that, if we call the speed of approach u, which is exactly what it is, the particle approaches W1 with speed u, then the speed of separation would be v, and we can find out what v is in terms of u. So we have the coefficient of restitution, that's 2/3. So we have 2/3 equals v over u, from which we see v is equal to 2u over 3 meters per second. So what does this mean? It means that the particle comes back with a speed of 2u over 3 meters per second. So we have 2u over 3 meters per second, and that's also the speed of approach to W2. So we have 2u over 3 meters per second. Okay? We can now find out the speed of separation from W2. The speed it's going back to O at. And we can do this again using this over here and noting that the coefficient of restitution is still 2/3. So we have 2/3 equals V dash, the speed of separation from the second wall, over V, the speed of approach to the second wall. And we can therefore see from here that V dash is equal to 2/3 V. Okay? And we already know what V is, that's 2U over 3. So we have 2 over 3 multiplied by 2U over 3, which is 4U over 9. Okay? Meters per second. So we have 4U over 9 meters per second. Okay? And we also should know that time is equal to the distance divided by the speed. Okay? So the total time, capital T. Now we have to be a bit careful here. If the particle is over here and it approaches W1 with speed U, its distance is d. So therefore the time is equal to d over u. Okay? And then from W1 to W2, that distance is 3 meters. And the speed, we've just found that out to be 2u over 3. So we have 2u over 3. And then going back from W2 to the origin, that distance is 3 minus d. So we have 3 minus d over that speed, which we've just found to be 4u over 9. And with this, we can end up rearranging to arrive at this. Now, the first thing we can do is we can bring this 3 to the top and this 9 to the top. So we have d over u plus 9 over 2u plus 9 lots of 3 minus d over 4u. And we can rewrite this d over u, we can rewrite as 4du over 4u. Hopefully you'll recognize the 4u's cancel on the top and the bottom. And here we have 18 over 4u. Hopefully you'll recognize 18 over 4 is 9 over 2. And then if we expand on the top, we have 27 minus 3d over 4u. And if we combine these fractions, here we have 4d over 4u. If we combine these fractions, we have 4d plus 18 plus 27 minus 3d divided by 4u. And therefore, if we simplify all this, you'd find we get 45 minus 5d over 4u. Obviously the units would be seconds. And now for part B, the value of u is fixed. The particle still hits each wall once, but the value of d can now vary. You have to find the least possible value of t. Giving your answer in terms of u, you must give a reason for your answer. Now, if we take a look at this formula over here, the least value of t we have will be when d is maximum, and d is maximum when d is equal to 3. Remember the condition for d is in between 0 and 3. Note this inequality here. So for part B, hopefully you can see that the least value of t occurs when d is a maximum, and that occurs when d is equal to 3. And the reason for this d equaling 3 is, if we go back, you'll recognize from this inequality d is less than or equal to 3. So knowing that d is equal to 3, we can therefore see that we have t equals 45 minus 5 times by 3 over 4u. So we have 45 minus 15, which is 30. So we have 30 over 4u, which is equal to 15 over 2u. Okay, units, of course, we have seconds. Now in terms of question 1, where we've got to find, where we have to show that t is equal to this over here, part A was done pretty well. Many candidates actually showed this result, but a lot of people made errors in not realizing that time is equal to distance over speed. I always write that down. It's a very basic fact that you should know from high school, but a lot of people fail to recognize that. Part B, where we have to find the least value of t, there were a couple of different approaches. Some people used calculus, some people drew it out. A lot of people did reach that conclusion of this value here, but a lot of people didn't as well. Okay. Some people simply argued that they needed to minimize the numerator of the fraction, and some drew a sketch of the function, and some tried to use calculus. I tried to minimize the function. Question number 2. We have figure 2, which represents the plan view of part of a horizontal floor where AB and BC are fixed vertical walls with AB perpendicular to BC. A small ball is projected along the floor towards AB with speed 6 meters per second on a path that makes an angle alpha with AB, where tan alpha is equal to 4/3, and the ball hits AB and then hits BC. Immediately after hitting AB, the ball is moving at an angle beta to AB, where tan beta is equal to 1/3. The coefficient of restitution between the ball and AB is E. The coefficient of restitution between the ball and BC is 1/2. By modelling the ball as a particle and the floor and walls as being smooth, we have to show that the value of E is equal to 1/4. Well, if we know that tan alpha is 4/3 and tan beta is equal to 1/3, I've drawn these diagrams to find out the value of sine alpha and cos alpha and sine beta and cos beta, and we can do that using simple trigonometry. So the first thing we need to do is, for this question, is resolve to find the different components. Before we do that, we can find this well, we can add this to our diagram. We have the impulse, and then here we have another impulse. We'll call this impulse I dash. Okay, now first thing we can do in this question is resolve parallel to AB after the first collision. So if we resolve parallel to AB after the first collision, then we have V multiplied by cos beta equals U multiplied by cos alpha. We know what U is, we know what cos alpha is. Cos alpha is 3/5, U is equal to 6, and therefore we have 6 multiplied by 3/5, which is 18/5. So if we add this to our diagram, here we have V cos beta equaling 18/5. And now if we resolve perpendicular to AB after the first collision, so if we resolve perpendicular to AB after the first collision, then we have V times by sine beta equals E multiplied by U multiplied by sine alpha. And of course, when we talk about V, we're talking about this over here. So we don't know what E is, we know what U is, so we have E multiplied by 6 multiplied by sine alpha, that was 4/5. So we have 24E/5. And if we know that tan beta is equal to 1/3, we know what cos beta is, we know what sine beta is. Of course, sine beta over cos beta, that's tan beta. And we can therefore use that to form an equation in E and set that equal to 1/3. So we have V times by sine beta over V times by cos beta, and this is equal to 24E/5 over 18/5. So it follows that tan beta is equal to 4E/3, and we can set this equal to 1/3, that's the value of tan beta, from which we see from which we see 4E is equal to 1, E is equal to 1/4. So what does this mean? Well, of course, here we have V sine beta, and we know that's equal to 24E/5. So we know that E is equal to 1/4, so we have 24/5 multiplied by 1/4, which is 6/5. And therefore V sine beta is equal to 6/5. Okay. And perhaps if it helps to add this to the diagram, here we have U times by the cosine of alpha, which we can find. We have 6 times by 3/5, which is 18/5. Okay. So we have u cos beta over here. Okay, now for part B we have to find the speed of the ball immediately after it hits BC, and when we talk about the speed we're talking about this speed v dash, and the first thing to recognize here we have an angle of 90 minus beta, and here we have an angle of gamma. Now we have to be a bit careful in this question. We have the different components. Here we have v, here we have v dash multiplied by cos gamma, and here we have v dash times by the sine of gamma, and then we can use Pythagoras to find out what v dash is. So the first thing we can do is we can now, for part B, resolve parallel to BC after the second collision. Okay, and if we do that, we have v dash multiplied by cos gamma, and that's equal to v times by the cosine of 90 minus beta, which of course we know from here will equal v times by the sine of beta. So this over here is equal to v times by the sine of beta. V sine beta we've just found to be 6/5. So we have v dash cos gamma equals 6/5. So if we add this to our diagram, we have 6/5 here. Okay, and we can now find out what v dash sine gamma is, and we can do that by resolving perpendicular to BC after the second collision. Okay, so if we do that, we have v dash multiplied by sine gamma, and this is equal to E dash, the coefficient of restitution between the ball and BC, multiplied by v sine of 90 minus beta. So we have E dash multiplied by v times by the cosine of beta, and hopefully that makes sense if we look here, the bit in red, and we know that the coefficient of restitution between BC and the wall, BC and the ball is 1/2. So we have 1/2 multiplied by 18/5, which is 9/5. Okay, so this component here is equal to 9/5. Now we can use Pythagoras to find out what v dash is. So therefore v dash, using Pythagoras, we have 6/5 squared multiplied by 9/5 squared square rooted. So if we work this out, you'd find we get 3 multiplied by root 13/5 meters per second. Okay, and now for part C, we have to suggest 2 ways in which the model could be refined to make it more realistic. So we can include friction between the floor and the ball. We can also consider air resistance. Question 2, that was all about basically I think it was a ball or something rebounding off walls. The part A of the question was to show that question sufficient to just to quote E tan alpha equals tan beta without explaining where the result came from. And I think what that means is essentially you have to resolve parallel and perpendicular to the walls to reach that conclusion. So in other words, show all your working. Part B, where we had to find the speed of the ball immediately after the second collision, complicated and required, and they did that by actually working out the different angles. There was no need. If you just resolve parallel and perpendicular like I did in the question, it was a fairly straightforward question. And those who did that like I did realized that it was actually a simple calculation to complete. And for part C, a lot of people showed good understanding of this, but this is a couple of interesting bits. Candidates should think carefully about the suggestions they put forward and not simply write down anything that they have heard of being relevant in this type of question. So don't just write down anything that you think is relevant, think about the context. Some of the suggestions were made irrelevant, such as the accuracy of G, and some are just completely incorrect. Question number 3. A particle P of mass 0.5 kilograms is moving with velocity vi plus 4j meters per second when it receives an impulse of I of magnitude 2.5 Newton seconds. As a result of the impulse, the direction of motion of P is deflected through an angle of 45 degrees. Given that I is equal to lambda I plus mu j Newton seconds, we have to find all the possible pairs of values of lambda and mu. If we draw out this situation, we've got some ball here, okay? Sorry, some particle P. And this particle P, if I write this down, that has a mass of 0.5 kilograms, okay? And that's moving with a velocity of 4I plus 4j. Let's just add this in. That's moving with a velocity, if we add this in, of 4I plus 4j. And then what we do is we hit this particle with some sort of an impulse. We give this an impulse of lambda I plus mu j, okay? And after we give this particle some sort of an impulse, of course, there's two situations which we need to consider. After the impulse, either the particle will move with a velocity of, if I write this down, the particle will move with a velocity of AI, okay? And the reason it's AI is because of this statement here. It's deflected through an angle of 45, so the 45 degrees is here. Alternatively, we could consider this in the j direction, so we have let's call it bj, okay? And I think it's important for you to recognize, for you all to recognize, that if it's deflected through an angle of 45, it can either move this way, so we have the 45 degrees here, or it can be deflected such that it moves this way. So we have 45 degrees here. So essentially there's two situations which you can model all this by. Okay? And if we consider the first situation in green, first of all, before we do that, if the magnitude is 2.5 Newton seconds, that tells us that the magnitude of I, that's of course equal to lambda squared plus mu squared square rooted. That's equal to 5/2 or 2.5. Okay, from which we can see that lambda squared plus mu squared is equal to 25/4. Okay, now if we consider this first situation in green where it's deflected by 45 degrees and therefore it moves parallel to the I direction, if we consider that, of course for this question we'd have to use I equals m lots of v minus u. In that first situation we have I equals 0.5 lots of 2ai. Okay, now the reason it's 2ai is 0.5 multiplied by 2a will give me the a over here, so just be a bit careful. Minus 4i plus 4j Newton seconds. So in terms of the I component, we have, if I multiply this through, we have ai minus 2i, so we have a minus 2i minus 2j. Okay, so if we know that the magnitude is equal to 25/4, sorry, if the magnitude is equal to 5/2, then from here hopefully you can see that we have a minus 2 squared plus minus 2 squared equals 25/4. Okay, and the second situation is similar to this as well. We have I equals 0.5 lots of 2bj minus 4i plus 4j. Okay, so we have in terms of the i's, we have minus 2i plus b minus 2j, and hopefully you can recognize that therefore b minus 2 all squared plus minus 2 squared is equal to 25/4. Okay, and hopefully here you'd recognize that we will end up with the same quadratic because A has been replaced with B. So if we form some sort of a quadratic in terms of x with these equations here, if we expand and simplify, if we have x minus 2 all squared plus minus 2 squared equals 25/4, so if we imagine that a and b are equal to x, because essentially these will lead to a very similar quadratic just with a different variable, we have x squared minus 4x plus 4 plus another 4 equals 25 over 4. And if we tidy this up a bit, we have 4x squared, and then here we have minus 16x plus 7 equals 0. And if we factorize this, we have 4x, sorry, no we don't, we have 2x minus 7 lots of 2x minus 1 equals 0, from which we see, if we solve this, x is either equal to 7 over 2 or 1/2. Now, this is where the difficult bit is. This tells us that either, if we consider the a value, so a equaling 7 over 2 and 1/2, if we consider these values here, then the value of I we can have, remember here the j is staying the same, that's minus 2j. If a is equal to 7 over 2, 3.5 minus 2, that will equal 3 over 2. So either I is equal to 3 over 2i minus 2j, or I is equal to minus 3 over 2i minus 2j. The reason for that is if we substitute in 1/2, then we have 1/2 minus 2, which is minus 1/2. That's one possibility. Of course, don't forget your units, Newton seconds. The second alternative is when b is equal to 7 over 2 and 1/2. In this case, the I component stays the same. So if we look at what b is, the I component stays the same at minus 2. Okay, that's in both situations. And then in terms of the j component, if we substitute in 7 over 2 and 1/2 into here for b, we've got the two possibilities of having 3 over 2j or minus 3 over 2j. Okay? And therefore, we've got our 4 different possibilities of lambda and mu shown here. Okay? Hopefully that makes sense. Question 3 was quite challenging for a lot of candidates. A lot of people could recognize that you've got an impulse momentum equation, but people together and the confused impulses and velocities. A significant number of candidates did make the key step of realizing that if the path of P had been deflected through an angle of 45 degrees, then the velocity must be parallel to I or J. And that's what we discussed here. There were 2 cases which we discussed. I think I wrote them down somewhere here. Some people, and if you did that, then you were often successful, but those who didn't do that and used a scalar approach, that gave complicated algebra and that often led to no conclusion. A lot of people found out the different values of mu and lambda as well. Some people formed simultaneous equations. Some people use symmetry to find out those different values. Question number 4. A car of mass 600 kilograms pulls a trailer of mass 150 kilograms along a straight horizontal road. The trailer is connected to the car by a light inextensible tow bar, which is parallel to the direction of motion of the car. The resistance to the motion of the trailer is modelled as a constant force of magnitude 200 newtons. At the instant when the speed of the car is v meters per second, the resistance to the motion of the car is modelled as a force of magnitude 200 plus lambda v newtons, where lambda is a constant. When the engine of the car is working at a constant rate of 15 kilowatts, the car is moving forward at a constant speed of 25 meters per second, and we have to show that lambda is equal to 8. Well, I've drawn out the diagram to illustrate what's going on, and you'll notice we've got this car. If I label this car, we've got the trailer here, we've got the forward driving force, we've got the resistance to the trailer. They are connected by I think a rope or something with a constant tension T, and the resistance to the car, we have 200 plus lambda mu. First thing we can do, we can find out what the driving force is using P equals Fd multiplied by V. So we have 15,000 equals Fd multiplied by 25. Fd is equal to 600 newtons. Okay, and if we're driving at constant speed, that tells us that the acceleration is equal to 0. And if we use Newton's second law, the sum of the forces is equal to the mass multiplied by the acceleration, where remember A is equal to 0, we have the forward force minus the resistance forces, 200 plus lambda multiplied by 25, maybe if I just write lambda V, minus 200, this is equal to 0. So we have 600 minus 200 plus 25 lambda minus 200 equals 0. So we have 200 minus 25 lambda equals 0. So lambda is equal to 8. That's exactly what we wanted to show. And now for part B. Later on, the car is pulling the trailer up a straight road inclined at an angle theta to the horizontal, where sine theta is equal to 1 over 15. The resistance to the motion of the trailer from non-gravitational forces is modelled as a constant force of magnitude 200 newtons at all times. At the instant when the speed of the car is v meters per second, the resistance to the motion of the car from non-gravitational forces is modelled as a constant, as a force of magnitude 200 plus 8v newtons. The engine of the car is again working at a constant rate of 15 kilowatts. When v equals 10, the tow bar brakes, the trailer comes to instantaneous rest after moving a distance d meters up the road from the point where the tow bar brakes. We have to find the acceleration of the car immediately after the tow bar brakes. Well, if we draw all this out, so what we have over here then is the car. Still has a mass of 600 kilograms. We've got the forward driving force and the resistance force. Remember, there's no trailer attached to the car because it broke off. First thing we can do, we can find the forward driving force, noting that V is equal to 10 when it breaks off, when the tow bar breaks off. So using P equals Fd multiplied by V, still working at a rate of 15,000. So we have 15,000 equals Vd multiplied by 10. Of course, Fd is equal to 1500. Okay, and if we now use Newton's second law, F equals ma, then we have the forward force minus the component of the weight, 600g sine theta, minus 200 plus 8v, and this is equal to 0. Again, the car is driving at a constant speed. This is equal to the mass multiplied by the acceleration. It's not moving at constant speed this time. So we have 1500 minus 600 g multiplied by 1 over 15 minus 200 plus 8 times by 10. This is equal to 600 a. Our goal is to find out what a is. So a is equal to, if we grab our calculator, we have 1500 minus 600 times by 9.8 times by 1 over 15 minus 280, and if I divide this by 600, we have 1.38 meters per second. Okay, and now for part C, we have to use the work energy principle to find out the value of D. Well, the work energy principle tells us that if I write this down, the work energy principle tells us that the change in kinetic energy is equal to the work done. And the work done, remember, is the force multiplied by the distance. So the change in kinetic energy, we have 1/2 mv squared. So we have 1/2 m multiplied by 10 squared. Remember, we're considering the trailer, so that's why we include this 150. And then we subtract off 1/2 times by 150 times by 0 squared. And this is equal to, well, here we have to be a bit careful. Remember, the trailer has a resistance of 200 newtons. So we have 200, and then we've also got the work done against gravity. So we have 150 multiplied by g multiplied by sine theta multiplied by d. So if we perhaps clarify this bit over here is the work done against gravity. Okay, so we have 7500 equals, well, if we work this bit out, remember sine theta is equal to 1 over 15. We have 200 plus 150 times by 9.8 times by 1 over 15, which is 298. So we have 298 d, and therefore d is equal to 7500 over 298, which is 25.2 to 3 significant figures. And don't forget, we have units of meters. Question 4 was a straightforward question, but it was a bit weird because some people either scored all the 4 marks or none of the 4 marks, as stated here. Part A, that a lot of people had correct solutions. Some candidates formed separate equations of motions of the car and the trailer and had to combine these in order to answer the question. The most common error was to overlook the constant speed and to assume a non-zero value for the acceleration. Where you've got constant speed, that suggests the acceleration is equal to 0. part B, where we had to find the acceleration after the tow bar brakes, a lot of people did not realise that they had to consider just the motion of the car then. Those candidates who only considered the motion of the car were pretty much successful. There were errors again in, if you use a value of g, then you have to round your final answer to 2 or 3 significant figures. Part C of the question, we had to use the work energy principle to find out the value of d. This is quite interesting. If you use the equation of motion or use SUVA equations, you scored 0 marks, and that's because the question said use the work energy principle. Some people use the trailer, but anyway, a lot of people lost the final mark because of the accuracy involved. Remember, we want to give it to 3 significant figures. Question number 5. A particle P of mass 3m and a particle Q of mass 2m are moving along the same straight line on a smooth horizontal plane. The particles are moving in the opposite directions towards each other and collide directly. Immediately before the collision, the speed of P is u and the speed of Q is 2u. Immediately after the collision of P and Q, P and Q are moving in opposite directions. The coefficient of restitution between P and Q is E. We have to find the range of possible values of E, justifying your answer. I think it would be a good idea to sketch this situation. Okay, so let's just do that quickly. So we've got P and Q, mass 3m and mass 2m. Before, they're moving with speeds u and 2u towards each other, and after, of course, they move in opposite directions. Now for part A, we can begin by using the conservation of linear momentum. So for part A, using the conservation of linear momentum, well, let's see what we have. We have 3m multiplied by u, and then we have 2m multiplied by minus 2 if we take right as positive. This is the situation before and after. We have 3m multiplied by minus v, and we have 2m multiplied by w. So this is the situation after. And of course the m's all cancel out. Hopefully you can see that minus u is equal to minus 3v plus 2w. I'll call this equation 1. And now if we use the impact law, that tells us that E is equal to the speed of separation over the speed of approach. Okay. So the speed of separation, we have w minus v. So we have w minus v, and the speed of approach, they're going towards each other, so we have u plus 2u. So we have here w plus v over 3u, and therefore hopefully you can see now that w plus v is equal to 3ue. We'll call this equation 2. Our next step is to solve equation 1 and 2 simultaneously, and we can do this in 2 ways. We can do this to find out what we can find out what v and w are in terms of u. So we can solve equation 1 and equation 2 simultaneously. So, if we solve these simultaneously, we can first of all multiply equation 2 by 3. So we have, if we do that, we have 9EU equals 3V plus 3W. And now if we add the equations together, so equation 1 plus equation 3, we have U lots of 9E minus 1 equals 5W. Okay, we'll call this 4. From which we can see W is equal to U over 5 lots of 9E minus 1. Call this equation 5. And if we substitute this back into equation 2, so 5 into 2, we have W, which is U over 5 lots of 9E minus 1 plus V, and this is equal to 3UE. So we have 9 over 5 UE minus U over 5 plus V equals 3 EU. So 3 EU minus 9 over 5 EU, that's 6 over 5. So we have V equals 6 over 5 EU plus U over 5. Hopefully you can recognize V is equal to U over 5 lots of 6E plus 1, and of course we know that E must be in between 0 and 1. So E must be in between 0 and 1, and therefore we're looking at the values for which W is greater than 0. So we have 9E minus 1 being greater than 0, E is greater than 1/9. And if you want to check when V is greater than 0, we have 6E plus 1 is greater than 0, and therefore E is greater than minus 1/6. And therefore the range of values, we have 1/9, which is less than E, which is less than or equal to 1. And that's our final answer for part A. Now for part B, given that Q loses 75% of its kinetic energy as a result of the collision, we have to find the value of E. So for part B, if Q loses 75% of its kinetic energy, then the final kinetic energy is equal to 25% of the initial kinetic energy. Okay? So the initial kinetic energy, we have 1/2 multiplied by 2m multiplied by the velocity squared, so we have the initial velocity u and then we square that, so times by 2u squared, so we end up with 4mu squared. And the final kinetic energy, we have 1/2 multiplied by 2m multiplied by, if we go back, multiplied by w squared. Okay, so we have m times by w squared. Now w, we've just found that to be u over 5 lots of 9e minus 1, So we have u over 5 lots of 9e minus 1 squared. So we have mu squared multiplied by 1 over 25 lots of 9e minus 1 squared. And if we use this statement here, we have the final kinetic energy mu squared multiplied by 1 over 25 lots of 9e minus 1 squared. That's equal to 25%. So we have 1/4. No, maybe if I make this clear, we have 25% of 4 mu squared. So this bit over here would correspond to this statement here. And you can recognize that the mu squareds cancel on both sides. So on the right hand side we have 1, and if I multiply that by 25, we have 9e minus 1 squared equals 25. 9e minus 1 equals plus minus 5. So if we consider the positive solution, we have 9e minus 1 equals 5, from which we see e is equal to 2/3. And if we consider the negative solution, we have 9e minus 1 equals minus 5, from which we see e is equal to minus 4 over 9. And therefore, because e is in between 1/9 and 1, we can therefore conclude e is equal to 2/3. In terms of question 5, a lot of people recognize that to use the conservation of momentum and the impact law to do this question. Those who drew a clear diagram often formed the correct inequalities. Candidates without a diagram were more likely to state an incorrect inequality, but some candidates with the diagram contradicted that. So I think it's just about recognizing the change in direction. The most common for part B anyway, which was something to do with the expressing the finding out the value of E. The most common errors were to form an equation about the total kinetic energy lost for both particles and to use the percentage loss incorrectly. Question number 6. A smooth sphere A has mass 0.2 kilograms and another smooth sphere B with the same radius as A has mass 0.4 kilograms. The spheres are moving on a smooth horizontal surface when they collide obliquely. Immediately before the collision, the velocity of A is 3i plus 2j meters per second, and the velocity of B is minus 4i minus j meters per second. At the instant of collision, the lines joining the centers of the spheres is parallel to I. The coefficient of restitution between the spheres is 3/7. We have to find the velocity of A immediately after the collision. So I've drawn out the situation here. We've got A and B. Before the collision, we've got the velocity of A shown here, and after the velocity of B shown here. After the collision, they join together, and then of course we've got the impact. The j component of A and B don't change, so here we still have the 2j, and here we still have the minus j, but in the I direction the velocity changes, and of course we have a common tangent and the line of centers. For this question, we can first of all begin by considering conservation of momentum parallel to the line of center. So if we consider the conservation of momentum parallel to the line of center, then we have if we consider the situation before, we have 0.2 times by 3. Remember, we're only considering the I components, so we have 0.2 multiplied by 3 plus 0.4 multiplied by minus 4, and this is equal to 0.2 multiplied by minus v, remember, consider the directions, plus 0.4 multiplied by w. Hopefully you can recognize minus 5 equals 2w minus v. We'll call this equation 1. And now if we consider the impact law parallel to the line of center, remember, for the impact law we have E, which is equal to the speed of separation, over the speed of approach. Okay. So we have w minus v as the speed of separation, and the speed of approach we have 3 plus 4. So we have w plus v over 7, from which we can hopefully see 7e is equal to, well, we know that the coefficient of restitution is 3/7, so this over here is equal to 3/7. Okay, maybe if we highlight that, E, we were told in the question, is 3/7. Okay, that's what we were told in the question. So if we solve over here, well, first of all we see that these 7s cancel, so we can hopefully see that we have w plus v equals 3. We'll call this equation 2. And if we solve equation 1 and 2 simultaneously, we can find out what v and w are. So we will now solve equation 1 and equation 2 simultaneously. And if we do that, well, we have w plus v equals 3, and then we have 2w minus v equals minus 5. Adding these together, 3w is equal to minus 2, and therefore w is equal to minus 2 over 3. And if we substitute this back in to either equation, for example in equation 1, we have minus 2/3 plus v equals 3. V is equal to 11 over 3. Now pay attention, because v is going in the opposite direction, and that's sort of standard to know, we can therefore conclude VA is equal to minus 11 over 3 in the I component plus 2j meters per second. For part B, we have to find the magnitude of the impulse received by A in the collision. Well, of course, just considering the I component, the magnitude of the impulse of A in the I direction, of course, so the magnitude of A in the I direction, we have m times by v minus u, so we have 0.2 lots of 11 over 3 minus 3, which is 4/3 Newton seconds. Part C, we have to find to the nearest degree the size of the angle through which the direction of motion of A is deflected as a result of the collision? Well, here we have to use the scalar dot product. So we have cos theta, which is equal to u dotted with v over the magnitude of A multiplied by the magnitude of v. So we have 3i plus 2j dot product with minus 11 over 3i plus 2j, and then we divide this by 3 squared plus 2 squared square rooted multiplied by minus 11 over 3 squared plus 2 squared square rooted. So if we work this out, on the top we have 3 multiplied by minus 11 over 3 plus 2 times by 2 over, and on the bottom if we work those out, we have 3 squared plus 2 squared, which is 13, so we have root 13, and then 11 over 3 squared plus 4, that's 57 over 9 if we, so then we multiply this by 157 over 9 square rooted. So if we work this out, cos theta, we have 3 multiplied by minus 11 over 3 plus 2 multiplied by 2 over root 13 multiplied by root 157 over 9. We get minus 0.464, etc. Theta therefore is equal to the inverse cosine of this, which is 117.699, etc. So therefore theta is equal to 118 degrees to the nearest degree. In terms of question 6, a lot of people saw questions like this before, and so were well prepared, and that's probably through looking at different papers from the old spec. The question asked for the velocity of A. Several candidates found out the speed without ever stating its velocity. Remember, velocity is a vector, and they did not state the direction of motion. A lot of people did not take into account directions. People complicated this more by working out angles in between probably the line of centers and the vectors. For part B, where we had to find the magnitude of the impulse, those who worked out velocities in vector form often got that right. The most common errors were working with speeds and not giving your final answer as a positive number, because it says magnitude, so you have to give your answer as a positive number. And for part C, you have to find out the angle of from the deflection. A lot of people who use a scalar product were often correct, but for this question, you have to recognize that you haven't, you weren't looking for an acute angle, you have to look for an obtuse angle, and you can do that by actually drawing out those vectors. And I thought it was obvious that why that was the case, but anyway, and obviously you have to give your answer to the nearest degree, because it says in the question something about a nearest degree. Question number 7. A particle P of mass m is attached to one end of a light elastic spring of natural length A, a modulus of elasticity kmg. The other end of the spring is attached to a fixed point O on a ceiling. The point A is vertically above O such that OA is equal to 3A, and the point B is vertically below O, such that OB is equal to 1/2 A. The particle is held at rest at A, then released, and first comes to instantaneous rest at the point B. We have to show that K is equal to 4/3. I think it would help if we sketch this entire situation. So here we've got our wall, our ceiling rather, and we've got the particle, and let's just show the particle in its equilibrium position. In its equilibrium position, let's suppose that the particle is in equilibrium here. Okay, then obviously you've got the particle here, and initially the particle is at the point A. So if this length here is A, so this is the natural length, so here we have A, then the point 3A, that's where the particle starts off at. It starts off here somewhere at this point here. So this length here we know to be 3A. This diagram's not to scale, by the way. And then the particle starts at A and then it goes to instantaneous rest at some point B. So this is the point B, and this length is equal to 1/2 A. Okay. Now, what could we say about this? What we have to do in this question is show that K is equal to 4/3. And for us to do that, there's a couple of things we can find. At this point, if we call this point Q, this point is the, rather if we move this here somewhere, if this point is the point Q, this is when the particle is in equilibrium. Okay, let's just also, and do we need to find this length? Not yet. Okay, so if we call this point Q, where this will be the equilibrium position. Okay, we might need that later on. And then of course we've got the weight of the particle, mg. Okay, and then we've got the tension here, T. So from A to B, the elastic potential energy lost is equal to the EPE gained. So the for part A, from A to B, the EPE lost is equal to the GPE, the gravitational potential energy gained. So if we use that, we have lambda, so we have lambda, the modulus of elasticity kmg, so we have kmg multiplied by the extension. Hopefully you can recognize that the extension from this point to this point is equal to 2a. So we have this squared, and then we divide by 2 times by the natural length, so we have 2 times by a, and then we subtract off kmg lots of 1/2 a squared, there's no extension, over 2a, and this is equal to mg lots of, well, here the difference between a and b, that would be 5/2. Okay, 5/2a. So that's that. Okay, so we have mgh, so we have mg multiplied by 5a/2. Okay, so the mg's cancel everywhere, so we are left with here 2k minus 1/8 k equals 5/2. The a's also cancel everywhere, so we have 15k over 8 equals 5/2, from which we can see k is equal to 4/3. Okay, so k is equal to 4/3. Now for part B, we have to find in terms of g the acceleration of p immediately after it is released from rest at a. So here we would have to use Newton's second law, F equals ma. So we have the tension minus the weight, that's equal to mx double dot. So we have the tension, so we have k, so we have lambda, which is 4mg multiplied by the extension, so 4mg/3 multiplied by the extension 2a over the natural length a minus mg. This is equal to mx double dot. So this bit here is the tension. Okay, so we have 8g/3. So we have 8g/3 minus g equals x double dot. X double dot, the acceleration, that's equal to, I'll write it here, x double dot is equal to 5g/3 meters per second squared. Okay, and now for part C, we have to find in terms of g and a the maximum speed attained by p as it moves from a to b. Now the maximum speed occurs at the equilibrium position. That's when we have no acceleration. Okay, so we have no acceleration here, and that's when we have a maximum speed. Okay, so the max speed occurs in the equilibrium position, and if we're in equilibrium for part C, so if we're in equilibrium, T is equal to mg. Okay, so we can find out what T is. That's quite straightforward. T is equal to kmg x, where x is the extension, over a, and this is equal to mg. We know what k is. That was equal to 4/3. So we have 4mgx over 3a equals mg. So therefore the extension x is equal to 3a/4 meters. Okay, so in terms of the diagram, this means then that this extension, if I show this in a different color, this extension from here to here is equal to, rather if we do it somewhere else, this extension from here to here is equal to 3a over 4. Okay, so that's the extension, and therefore this length, if I grab a different color, this color, so from here to here, this length here therefore will equal, well, we have 3a minus a minus 3a over 4, that's 5a over 4. So we have 5a over 4 here. Okay, let's just write this neatly. Here we have 5a over 4. So what does this mean then? We can now use the conservation of energy to form an equation to find V. So now for part C, if we use the conservation of energy, well, at the point A we have the EPE, so we have 4 mg over 3 multiplied by the extension 2a, then squared, and then we divide by 2 times by the natural length, so we have 2a, and this is equal to at the point Q, well, we've got the at the point Q we've also got EPE there, so we've got 4 mg over 3. Remember, 4 mg over 3, that's the modulus of elasticity, and then we multiply this by the extension over here, which was 3a over 4, so we have 3a over 4 squared, and then we divide this by 2a, and then we have the kinetic energy 1/2 mv squared, we're solving for v, plus mgh, so we have mg multiplied by h, which is 5a over 4. Okay, the m's cancel, and if you rearrange for v is equal to, if you use a bit of algebra, we have 5 over 2 multiplied by ga over 3 square rooted. Okay, so that is our final answer. So the maximum speed therefore is 5 over 2 lots of the square root of ga over 3 meters per second. Okay, so that concludes the end of the questions. For question 7, a lot of people had to recognize that they had to use energy. A lot of people initially treated the spring as a string and omitted the second term for elastic potential energy, but the answer given helped them to realize that their error, I think that was that, and then they corrected their errors. A lot of people forgot to use the kmg and they did not give a conclusion as a result of that. That's over here. Part B, a lot of people formed an equation of motion like I did over here, F equals ma, and they got the final answer from that. You have to, the question makes it clear that you have to give your answer in terms of g. Some people use decimals instead of fractions. It's easier to use fractions. Part C, that was quite difficult. That was where you have to find the acceleration of p. Sorry, that's where you have to find the maximum speed. you have to recognize that the maximum speed occurs at this equilibrium position. There were sign errors, etc., but if you formed a correct equation of motion, that was quite easy to do.